All right, guys, why don't we get going? So my name's Shawn Scully. I'm with Datto. Today I'm going to talk to you about production and what production means for machine learning applications. Super excited to be here talking to you guys. So what does production in general mean? I was actually surprised. There's not a very common definition online for even general code in production. But I like this one, which the core piece here is that production code is code that's being used by the intended audience in a real-world situation. So today we're going to talk about the different ways that you use machine learning code in production for a real audience in the real world, and what factors matter for machine learning services. Who knows who Datto is? Awesome, about half of you. Who went to Brian or Rajat's talk in the last couple of days? Cool. So you know the general gist. Datto, we were originally called Graph Lab. We were an academic project about 8 years ago, 8 years in the making. And we've been a company for about 2.5 years. We're up in Seattle. We're a team of about 45 or so. About half of us are PhDs in machine learning, statistics, distributed systems, and the other half of us have built real-world machine learning applications for a real audience and deployed to production for various things. And we're excited about building tools that make it easier for other geeks like us to build applications. We've been selling our stuff since the beginning of the year. These are some of the customers that are willing to let us say they're using us in production. Okay, and I'm not going to give you a big marketing spiel today, but in general, people like our stuff because it makes them more productive. So machine learning in production, there's really kind of two ways applications end up affecting business or affecting people's experience in production. And they're two very different ones. So the first one here is what we'll call batch materialization, or it's sometimes just called batch production. So in this case, there's two examples here. One is from Quora, and one is from Living Social. Both of these are emails that get sent to me on a daily basis. And so if you think about what's running behind the scenes there, basically each day, some sort of data pipeline crunches some stuff, and then a ranked set of things is written to a database, and then that database is turned into an email. A query is turned into an email, and that email is sent to me. And basically nothing happens in between those two sends. So it's just a daily batch job that gets run and sent. So that's one example. And in principle, the machine learning here is personalizing this email. So this is generally a case used for kind of all email targeting. And apparently I'm really interested in what it feels like to be fired from Google. I don't work at Google. I've never worked at Google. Okay. So what's another example? This is sort of the other kind of machine learning in production, and this is called a real-time service. And for this, I'm actually going to create, let's use one. So one of the first real-time services that we've used and experienced is online recommendation systems from someone like Amazon. And so if I go here, in real time, oh, it's remembering this. Let's get rid of this. All right. Oh, you can't see. Okay, it's good. It's worthless. Give me 1 second, and I'll show you. Okay. Displays. Okay, and you can see this, good. So if I go to Amazon, everything I do is watched. And let's say, so right now, if I go down here, I have no recently viewed items, and there's no recommendations for me. If I click on something, let's say this camera, so now when I go down here, let's Let's see. Now when I go down here, I viewed this. So your recently viewed items and featured recommendations. So I viewed this camera, and now it's giving me real-time recommendations that are related to that thing that I just viewed. And in this case, it's all things camera because this is the only thing that's known about me. If I click on other things, these things will change. And so let's say that I am a video game freak and I can't wait for Halo 5. If I click on this, I go back to my recommendations, and now I see that this is dominated by video games. So that's a different kind of machine learning application that's in production, which is one that's live and responding to my interactions live. So we're going to talk about both of those, but focus on the latter. So for both of these involve what I'll call a model pipeline, sometimes called a data pipeline. And so this is connecting the initial data. In the case of the Quora example, this was basically all of my interaction with various pieces of content on Quora, all the text, the documents. In the case of Amazon, this was just a simple click log. What did I interact with? So I take in that data in whatever form it is. I bring it into some place that I can manipulate it. Generally, I'm going through some sort of set of transformations, and then ultimately I'm doing some modeling. And if I'm lucky, that modeling gets deployed in one of two ways. And these are the two ways that we saw. So in one case, I could take my model, deploy it as a service so that that service can interact with something like a user's behavior on a website. In the other case, I generate predictions or a ranked list of things, and that ranked list of things gets written to a database. So this is called a model pipeline. And for the second case, what we're really looking at is a service. So if I take a model and deploy it as a service, whether it's a new experience like product recommendations or a machine-to-machine service like fraud detection, the idea is I have a low latency REST service that's waiting for an input and then returns some sort of prediction back. And there's a bunch of different examples here. I'm not going to go through all of them, but product recommendations was one that we looked at. A really fun one is for online gaming. They have an application called microchurn. Most all gaming companies use this. And the goal of this application is to maximize your time in the game. And so what it does is it watches every little move you make in the game and then dynamically tunes the difficulty of the game to keep you maximally engaged. So what it's doing is it's waiting, it's looking every, it's of order seconds, so every 1 to 10 seconds, it's making a prediction of how likely you are to leave in the next minute and then dynamically tuning. So that's a very different kind of real-time application. So how do you go from that model pipeline to a real-time application, and what are all the pieces involved? We call this the intelligent application cycle. So here's the model pipeline, which goes from data to a trained model. And then for a real-time service, ultimately you're trying to interact with some sort of other application or service. And that means that you need an interface. Here, these are typically REST interfaces. These work pretty well. And then once you have something deployed, typically you're looking at how does this thing work in production? Are my users responding in the way that I expect? Are the click-through rates moving in the way that I expect? And if not, I want to change something. So I want to monitor those things live. And then production usually is about retraining these. Just like Quora or Living Social, you get new data each day. You want to re-rank. You have new data, new items, new things to respond to. And so you need to retrain those models. And then finally, in most places, I have super awesome data science teams that are working on the next great feature or model that's going to also get deployed. And for that, once I deploy those, then I want to monitor, model A versus model B, or maybe I want to launch a series of models altogether and let the best one win. So these are all things that you care about in managing that whole end-to-end life cycle. Okay. So what are some of the challenges in running some of these things in production? The first is just that we all have time constraints, whether it's the time to develop something, or as the case for these applications, we have a bunch of steps that need to run fast enough. Very simple. The second is that the world's constantly changing. Whatever data I use to train my models, as soon as I've trained my model, the world's changed and the model's out of date. And so you need to be able to quickly respond and adapt to changing data. Unfortunately, we have to play well with others. And that basically means other systems. So there's a classic problem that everyone sees. If you have a data science team that works in R and then a production application, let's say, that's written in Java, how do you get these guys to talk to each other, both in terms of people and in terms of systems? And then it's also the case in many companies that when I go to production, when my new feature or model is in production, it means that I'm handing it off. It often means that they need to understand whatever I did. So this is very, very similar to any kind of code that's pushed to production. For demanding, well, for any application really, the other requirement is it needs to be robust. It has to just work. You have to be able to walk away and have your application continue to work well without you babysitting it. And then the last one, I'm not going to talk so much about this today, but it's a really important one. It's that live machine learning doesn't always match up with your offline predictions. So has anyone had the experience of training models offline, thinking that you're going to have this huge lift in your advertising strategy or click-through rates, and reality doesn't match up? And that's a big problem, which often comes down to what metrics are right offline to map to your online setting. It's not always obvious. So we're going to focus on these other ones today. So what kind of time constraints matter? How do you think about that? How do you deal with the fact that data is constantly changing? So when people talk about real-time machine learning, what do they really mean? What do you really need in those contexts? What's important to play well with others? And then finally, what do large-scale services, what are the requirements to make these robust? Okay, so responsive. So at the end of the day, when we make these kinds of, that's funny, it's not showing up here. When we make these kinds of services, there's a few key ingredients to make them awesome. The first is that they're responsive. So when I'm on a site, I click something, I get a response back really fast. The second is that they're adaptive. So we respond to changing context, whether it's in my session as a user or changes in data. There's lots of new news articles that came out and we need to respond. And then the final one is that it's manageable. So it's often the case that I don't just have one model in production, I have many, and I have a team of folks that are sharing infrastructure and sharing production systems. All of these matter. Okay, so before we talk about responsiveness, let's talk about times. When we go back to this life cycle, there's a few times that matter, and they often get conflated. So what's the first? The first is the time to respond. You often call this the requirement for latency, or the latency time. So this is basically the time associated when a user or a service queries your predictive service, and you get a response back. So that's one important one. Another important one is the time it takes to train a model, or the time it takes to train a pipeline. This relates to how quickly you can update given new data. Another one that often matters, which most of us don't have a good idea of how to quantify, it's how long does it take my team to develop a new model or a new feature and then get it to production. There's many things that matter there. It's not necessarily a systems constraint. It's more of a how we do data science and machine learning as a business problem. And then the final one here is also related to being adaptive. If I have many models that are running in production, and let's say that I have a model for me as a user when I'm shopping for myself versus me as a user when I'm shopping for my mother. And you can imagine if I'm on Amazon, I might be clicking on different things. And so based on different features, you could have a policy set up that says when certain features are detected, you're going to switch to the model that says, I am looking for a present for my mother. So there's a time associated with learning those updates. So each of these are different, and they require different things in your system to have those times be short enough. OK, so how about addressing latency? How fast is fast enough for queries? So you have to ask the question for what? For queries. So in the case of online recommendations, something like Pandora, this is for a good experience. So fast enough for a good experience. For ads, this is fast enough to score, bid, and win the ad placement. Or for something like credit card fraud, this is fast enough for the transactional decision. So you swipe on a Square point of sale thingy, and there's a 30 millisecond window to decide fraud or not fraud. So all of these have different timescales associated with them. So for online recommendations, for a good experience, this is basically fast enough so that it doesn't seem slow as a human. And that's somewhere around 300 milliseconds, unless you're a super person. And then for ads, this is faster, somewhere around 60 milliseconds. And then the most demanding typically are in the financial services sector. OK. So different timescales matter for different models and different applications that you're building. So what's the challenge in scoring fast? So if I want to compute predictions in less than something like 20 milliseconds, so I can be good for all of those applications, for complex models, what matters? Or there's various things that I care about. Complex models, so this could be something like gradient boosted trees, and I want to make a prediction on fraud or not fraud, and maybe I have many, many factors involved in my feature vector. This could be queries, as is the case for recommendations. So here, it's typically the case that I don't care about making a relevant score for all items and users in my library, but just the ones that are at the top. So for me, Shawn, Scully, give me a top K recommendations, let's say, of the top 100 most likely things that I'm going to click on out of a library of maybe millions. I don't have to score for all of those. I just care about a fast query to get those top K. And then the final one is for features. So this could be about fast querying of a set of history or a set of contextual information that's going to be relevant to input from my models. And then all of this, you have to be fast when I have not just one query, but let's say 5,000 queries a second, because I have a really large scale service with many, many users. So what are the common solutions to low latency? The most fundamental is just faster models. So how do you get faster models? Well, you have really good implementations that are written in native code. And native code scores faster than interpreted code. And so that's one option. The other option is what might be called pre-materialization, which is a big word which really just means caching. So this is about certain queries that come up over and over again. If you cache those responses, then you don't actually have to call a compute. You just call a lookup for those queries. So for us, for faster online model scoring, we do this, if you attended Rajat's talk, you heard about our S-frame and what we might do with model querying. So our stuff is all in native code. It's all in C++. We have a very, very thin Python wrapper on top. And then that native code is optimized for exactly these kinds of queries so that when I have a low latency requirement, I can score fast. S-frame is built for that, but then the other is for fast querying. It's about how you implement the predict function of your machine learning models so that you're not predicting for all things, but only the things that matter for that query. The other case is for caching. So let's talk about that for a second. So smart materialization. If you think about So I'll ask the question to you guys. So if we think about Amazon as an example, what is an item that you think might be good to cache here? Anyone from the audience? Trending items, exactly. So items that are popular, many people are going to be clicking on them. And so it's rarely the case that you want to have a computation done for each new user that comes and clicks on Harry Potter as an example. And so that's a case where if you just have that answer stored, you can utilize that. And it turns out in most cases, most queries, it's sort of a circular thing, most things that are popular are things that are queried lots. And so for a small number of items, if you cache a small number of items, you can take care of a whole lot of your load for the case of something like recommendations where someone's clicking on something. So that's an application that makes sense to use caching. There's other applications where something like fraud detection, where each transaction vector that comes in is going to be unique. And so in that case, caching doesn't make sense. But for things like recommendations, where I have many users and a small set of items, relatively speaking, this is super important. And then there's when you build this in the right way, it turns out you get some other features for free. So in this case, if I have a huge load of folks, or if I have a huge load coming into my predictive service, it often makes sense to have a cache that's shared across many nodes. And so we call that a distributed cache. In our stuff, we use Redis as a distributed cache. And what's great about this is basically if one of the nodes in my cluster goes down, I have those answers stored across the cache. And so I get redundancy for free. So when we talk about heavy load coming in, this is, I guess I jumped ahead. So let's say I have something like that recommender service. I have tons of folks that are all wanting to click on Harry Potter. If I just have one machine at a certain load, this service will slow down, and the queries will pile up. And so the solution to this is to do what's called scale out. And you can use something like an elastic load balancer to handle traffic routing, to distribute those queries across many machines. And so this is one of basically the standard way that anyone handles high volume web services. But then what happens, what are the other things that I care about when I have many nodes and high throughput? I care about what happens when some of these go down. And so then you want to do things like be able to easily recover nodes when they go down. And that's about doing things like storing state associated with each of those nodes. OK, so that basically wraps up being responsive and what you care about for being responsive. So you care a ton about fast model querying, which generally is going to lead you to fast implementations of certain models. And you care about caching for certain applications. OK, what about adaptive? So responsive, adaptive, manageable. Adaptive. The question is to or for what? So how fast do I need to adapt? Let's start with a couple thought experiments. So let's say that I have a recommender with tons of historic data. So this is a recommender with, let's say, 3 years of data. And I've trained that up. Has 100 million events, 50,000 items. And then this has been running now for another X days, and I have 1 million new events. Tons of events with the same 50,000 items. Is this a case where I need to update quickly, soon? How should I think about this? Is it out of date? Am I screwing myself by not having the model update? No. Because the deal is the data that I've just added is just this tiny little blue sliver of data. And if it's on the same distribution of items, and if in general I'm making the assumption that the users are basically the same, nothing's changed in the world, except I have more of the same, probably the model's not going to change a whole lot. If we take a look at a recommender that's only using recent data, this is a very different example. So maybe I've trained a model using only yesterday's events, and now I have today's events. Well, now my new data matters a ton, right? And it's very likely that things could have changed. So this is a case where I care about updating a lot. But here's another case where I care about updating quickly. So I have that same historic data, which is lots and lots, and I've gotten new data for the same stuff, and I've added 100 new items to my corpus, to my library. So in this case, for those 100 items, things have changed. Those 100 items I have no data for before this, and so it's going to matter a ton to retrain or update my model or change the strategy for how I handle these new items. So when to update, these are very simple examples, but they're useful to think about when we're thinking about the different systems and when to update them. So when really depends on ultimately my model performance. When is my model no longer good enough? So if I went back to this example here, the other thing that would help guide me is tracking some sort of online metric over time. And if I see that things are trending down, that's going to be a good indication that I need to do something. So when is my model no longer good enough? When do I have a better model? So that's more about my data science team, and when do I have something better to deploy? But what we just talked about is about basically data velocity. How much is my data changing? How much has the world changed? And do I need to incorporate that in my model? The other is just time relevance. So it could be the case that we have an application that's specifically about yesterday's news or today's news, in which case updating at that time matters. Okay, this basically, this is one piece of being adaptive. The other is thinking about all of the things in the world or my user's experience that changes and how they change at different rates. And so if I think about things like seasonality, what's happening in the markets, these are things that generally have pretty long lifetimes and change on the order of, let's say, months. There's other things that change faster, going all the way down to the case where within a session, I might be in a mode where I'm shopping for a new shirt for myself, but I also want to buy a present for someone. And so how could I have an application that's smart enough to recognize when I'm in two different modes of search, right? And in this case, the timescale is more of the order of minutes or so. We're wanting to respond to our users. So for the large things, or the slow-moving things, large things typically move slowly. And so in this case, you can typically just rely on retraining your models offline. And it's often the case that I'll use A/B testing to look at strategy A versus strategy B. For things that are more recent, this is smaller data. Smaller data generally changes faster. And this is the case where we care about things like online learning or using things like bandits to assess how our models are doing and dynamically change the strategies that I'm serving. So it's totally reasonable that you could have a strategy that adapts, that based on my real-time interactions, figures out that I'm no longer shopping for myself, I'm shopping for someone else. So when you think about that, what matters is feedback. And there's some funny things about feedback and machine learning. So we started off with cameras and Amazon.com. And as it turns out, Amazon's been getting smarter about this. But I once looked at cameras. From then on, for a long, long time, I was only ever recommended basically other cameras and other camera-related stuff. I don't know how many cameras you have at home, but typically I only have one, maybe two at any given time. And so what's really important here is being able to dynamically explore other things that you don't have information about. So this is for certain items, this is a pretty bad recommender, right? And so ultimately, when you're building machine learning services, you care about something like trade-off between exploration and exploitation. And that's exactly what multi-arm bandits are built for. The strategy is basically take some of your queries you're going to exploit. You're going to use what you know works well. In this case, this could be the recommender system that's working well and giving me other cameras. And then the other percentage of the time or percentage of slots that I'm showing, I'm going to show new things that I don't have information about to explore other interests that I might have. And you can either be really simple about that and do sort of random exploration, or you can be smart about that and do things like show maximal diversity in those other spaces. And that can be super, super key. For things like online e-commerce, this matters a lot. So what are some solutions to adaptivity? For us, it's all about time scale. So the question is, how fast do you need to update your models? So it's important to have rapid offline learning. And that's about being fast enough to keep up with how much the data's changed. So that's about running model pipelines and deploying new models. Streaming features, we didn't talk about this. A lot of people talk about streaming. Streaming, do you do streaming? Do you do streaming machine learning? And most people that are asking about that, they're trying to figure out, well, what's that actually mean? How does that map to the applications that I want to build? Because everyone's talking about streaming, and so it must be important. Where I see streaming fitting in is really in features. So in cases where, as that example where in-session behavior, what you want to do is have some sort of aggregate of my behavior over a certain time window. And it's that aggregate that you're changing, that you're updating in real time, so that can feed into your model and then make a prediction. It's actually about the input data being streaming rather than model training being streaming. Another case here, this is used for fraud, often where what you're looking at is sort of what are credit card transactions looking like across our entire transaction network over the last, let's say, 30,000 transactions. And so you're accumulating statistics that are basically a moving window that you're then using in your anomaly detection applications as a feature. So streaming features matter, not in the way that most folks talk about them. And then the last one we just talked about is online bandits to adapt for things like in-session feedback. And what's important there is that you have a framework that's flexible enough to basically implement your own cost functions for how you're going to move between different models. Okay, manageable. I'm not going to talk a ton about this, but manageability for machine learning models is really just about making it easy for your systems and your code to play well with others. And when you think about times when I've built these things, I use many different things. Especially if you start off as a data scientist and you kind of pick up development skills along the way, your stuff often starts off looking like spaghetti. and usually you have to spend a lot of time with some production engineers to make that production worthy. At the end of the day, these systems tend to be pretty complicated because we're using many, many different things, all of which have many different purposes. They overlap, and that's hard to manage. The other things that you care about, besides just managing different systems and a code base, are things like provenance and reproducibility. So for code, we have things like GitHub. For models, you care about things like sharing models, knowing when they were created, having all of the meta information describing what data set was used for what model. So that's important. Being able to collaborate with the production system is important because usually it's not a team of one that's building and deploying new applications. And then the final thing is that things should just work such that they're continuously integrated. So that's about having a system set up that's automatable. So for for Datto, we talked about the intelligent application cycle. We have tools specifically for this whole cycle. GraphLab Create's all about building models and efficient training of model pipelines. You heard probably lots of stuff from Rajat and Brian about some of the cool things that are there. And then Data Predictive Services is all about serving models live as services. For some folks, if you have to go to ultra scale and that time to run a model pipeline is taking too long, you can use distributed machine learning. We have some implementations of that. So this is my last little pitch for us. If you're interested in building applications with us, this is kind of how things map out. So for predictive services, we have an architecture that has a load balancer and a scale-out architecture. We have model management built in. We have caching for those repeated queries for low latency. We're responsive, so for things like boosted decision trees, we're under 10 milliseconds for sort of reasonable models. Super high throughput, manageable. I didn't show it here, but the other thing that typically matters in a lot of teams is being able to take, I'll often have a team that cares about deploying, they care about modeling in scikit-learn, another team or team member that cares about modeling in R. So being able to deploy both of those in one system is key, and we've built things to support that. And then finally, being able to easily take those models and integrate them into your other applications through something like a RESTful API is crucial, and we have all that. So if you're interested, I didn't have a demo today, but grab us out in the hall, and we'll show you how to deploy scikit-learn models. With that, I'm happy to take any questions. Yeah.
So for customers that give you their data to do the prediction, do they give you like raw production, operational data, or is it clean and data warehouse? Or?
I made one big mistake, which was when describing this, not reminding that basically this deploys on your infrastructure. So we're not a cloud service. It's your machines running our software, but it's yours to manage and deploy. So we actually have no idea what's going on with your data. Yeah. Other questions? Okay, cool. Well, come grab us outside, and more than happy to talk.